guys, continuity of Bernoulli's equation. So what happened was I was shooting this video and I taught a lecture here. Apparently the memory card got full, so it recorded only like first 12 minutes of my lecture. So I'm gonna re-record here, okay? Continue our Bernoulli's equation. That's what I mean to say. So Bernoulli's equation. Bernoulli's equation. Okay. So let's draw a diagram here. Again, just we have a pipe, tube. Okay. And we have a fluid. Okay. So let's consider cross-sectional area A1 and at this point here. Let's call this point as a 1, okay? So we are just referring here. Point 1. This has a cross-sectional area A1. Assume the fluid through this tube. Assume there is like, fluid here going like this, and then this is a cross-sectional area A2. Let's assume this point is a 2, okay? So I'm just going to write here point 2. And there is fluid, right? More fluid here. Just making more fluid here. Okay? Now, what we are going to do is this, guys. So first of all, we are going to look at, we are going to see how much of the volume of the fluid is going to flow in this section here. And we'll take like a small distance delta x here in this point 1, reference point 1, and then compare that volume with the amount of the volume that's here, okay? That moves in this tube through here some distance, maybe delta x2, in the same amount of time. So the important thing is we are talking here about the same amount of time, right? Delta t is constant or same duration. Or if we are thinking, if you're looking at this tube, how much of the fluid is flowing in 2 seconds here, first let's say 2 seconds, then we want to look at the same time frame here also. So in the same 2 seconds, how much of the fluid is flowing in this tube? That's what we mean, okay? We are looking at the same constant delta t here. And then we are going to apply conservation of energy equation, special form of the conservation of energy equation, and then look at what we are given here and try to play with the equation a little bit and then come up with Bernoulli's equation, okay? So before we do all of those, let's make a coordinate point here. So let's start origin. If origin is here, this is our y-axis. Let's call this point 1, this height here is, so this point 1 is at height y1, y1. This point 2 here it is at a height, I'm gonna just make a height distance here, okay? Alright, maybe here, y2, okay? You could also just make it over here, it doesn't matter, okay? So they are at a different distance, different height from the origin. So this fluid is moving with some speed. Let's call v1, right? Okay. It's moving with the speed v1 here. In some time, some delta t. So let's consider some same time delta t, and in that time it covers the distance. Let's make another cross-sectional area here, so it covers this distance here, okay? So let's call this as delta x1. Maybe I'll write this delta t a little bit up. In that delta t time, the fluid element covers this delta x1 distance. Now, if you remember from continuity equation, the volume, let's call delta V, change in volume or volume element here, volume of the fluid flowing from this distance is what? We have a cross-sectional area A, right? And we have a distance, so it becomes tiny cylinder like this. So like this, we have a, it has a cross-sectional area A, and then we got this cylinder, and the length of the cylinder is like delta X, okay? So the volume becomes, delta V becomes simply area times delta X, alright? So the volume is what then? A1 times delta X1, alright? Now, we also want to say there is a pressure, right? Because it's at some height, right? There's some fluid here, it's at some height. So there is a pressure on this, end here. That pressure is P1. Let's call it P1. This pressure, there is a force on this end due to this pressure, right? So there is a force pressure. Because of that force pressure, fluid moves here in this tube, okay? That part is what we didn't have in continuity equation. So this pressure, we can write P1 equal to what? Let's say force. That force that's acting on this end is something like this. So there is this force F1 that's, due to pressure 1. So that is what? F1 by A1, okay? So we know now, we have these quantities. Now, this all happened in some time duration delta t. We want to do the same thing here for this point 2. So again, we have area 2, it's, the fluid moves with the speed v2, and then the volume amount of the fluid that is flowing here in the delta duration delta t is delta v equal to what? A2 times the change, right? So because A2 times the distance it moved, look at this. How far will it move? Do you think it will be same distance as delta x1? What do you think? This is a wider tube, and then in the given time, I don't know, delta t, it is moving through this distance delta x1. But this is really narrow, right? In the same duration, the fluid here must move further away, right? Which means this would be somewhere maybe like this. Let's make it a little bit further away. Okay, so this fluid moved here, this distance. Let's call this distance as delta x2, okay? So, delta V, or change, the volume element here is equal to cross-sectional area times, again, delta x2. Same idea, right? We have a cylinder, but it's kind of a longer cylinder with the, smaller diameter, okay? Alright guys, and then there is also pressure P2, which is equal to force F. There is a force here, right? So the force is actually, before it really moved, the force is what? Right? There is a pressure just because they are at different height, though the force is due to pressure is actually in this direction, F2, okay? So this is important because the movement of a fluid happened afterwards, but before there was just a fluid, and then we had a pressure when the fluid was just sitting there without moving. But once it starts moving, then it is moving through the distance, right? Now there is not change in pressure because it's again moving through the same distance. This is important, okay? So our here P2 equal to what? F2 by A2, okay? Alright guys. Okay, so now we kind of finished labeling. Now next step is to apply conservation of energy. So from conservation of energy, we can write change in kinetic energy delta K plus change in potential energy must be equal to work done on the system. Our system is the fluid inside this tube, okay? So let's call this equation 1. Let me check this video real quick in case, you know, again the memory is full. I just want to check and come back. Alright, that looks okay so far. I'm gonna check again in another 5 minutes and hopefully it won't betray me like last time. Alright guys, so now our job is to this. Find the kinetic energy at that point 1, find the kinetic energy at point 2, find the change in the kinetic energy between this point 1 and 2, and then do the same thing for potential energy. Find the potential energy at point 1, find the potential energy at point 2, find the total change in potential energy, and we'll also do the same, find the work done when the fluid was moving from here through this distance delta x, and we'll also find work done when the fluid was moving through this distance delta x2. And then we add those work done to find total work done W. And then whatever the expression we get, we are going to put it back to this equation 1 and then just rearrange it to get Bernoulli's equation, okay? So let's do this. Alright, so now I'm just going to write delta K, okay, meaning change in kinetic energy. Let's look at point 1. What do we have at point 1? K1 equal to what? Half m1 times b1 square, right? Mass times the speed here, square of speed. But what is this mass, guys? Do you guys remember mass? We don't really know anything about mass. We are not given anything here. So what we do is, let's say at least we know this fluid has a density rho, okay? So this is the density here. So density rho equal to mass by volume, right? So in place of mass, m1, we can write rho times v, at least we call here delta v, okay? So we could just write that one, right? Okay, so m1, in place of m1, we are going to write rho times delta v times b1 squared. See this b1 and delta v, this is not same, okay? This has a little bit of that twisted side, that is the speed, this b is just regular b like this and then be like that, okay? So those two things are different here. This is volume, this is speed, okay? Alright, so let's not call anything right now. Let's find the kinetic energy K2 for point 2. We should have again similar equation, half m2 times b2 square. I don't even need to look at there anymore because I know mass, right? At this point, what do we have? We will have mass is equal to again rho times b. Density is constant for that fluid. This volume is also, change in volume is also constant, right? So we can just write rho half times rho delta v, but b2 has to be written here, okay? So that is our kinetic energy at point 2. Now, fine, let's see the total change in kinetic energy K equal to what? How do we know which, whether to subtract or add or at least which one goes first? So let's look at this. At this point, the tube is really wide, so the speed of the fluid is slow. At this point, the tube is very narrow, speed is really fast, which means this speed must be greater, right? So we are going to do K2 minus K1, and that is going to give us, this is going to give us half rho delta V, B2 square minus half rho delta V, B1 square. Now let's call this equation 2. Okay, now for change in potential energy delta U, what is our, I'm going to use the other color, guys. This is kind of fading away. Delta U equal to, so what is our U1? What is the potential energy at this point here? You guys remember potential energies was mass times z times height h. So our mass at point 1 must be m1 times z times our height is what? y1, right? y1, which is equal to what? In place of m1, again we would use the same thing like rho times b, delta v in this case, rho delta v g y1, okay? Similarly, we can find u2 equal to m2z y2. And then again, as you know, M1 and M2, they are same here, so rho delta B Z Y2. So from this we can write down the equation for delta U. Now, should we subtract U1 from U2 or U2 from U1? So again, potential energy, it's at a lower height, right? This has a higher height, so this one has a higher potential energy, so you have to do U2 higher minus lower value, okay? So U2 minus U1, and then you end up getting rho delta V Z Y2 minus rho delta V Z Y1, okay? Alright guys, so this is our equation 3. For work done W, what is our work done W1? Do you guys remember anything about how to find work done? So work done is basically given as what? Force times the displacement, right? So delta x, right? Now this will have a negative sign here if the force and the direction of the application of force and the change in the displacement are in opposite direction, then we will have a negative sign. But if they are in the same direction, force and the change in the displacement, then we will have a positive sign, right? So work done is just F times delta x. So work done, what is the work done in moving a fluid? First of all, what is doing the work here? Guys, this is important. What is doing the work here? This is the pressure force, okay? That force F1 is the pressure force, right? This pressure force is doing the work, okay? So then there is a work done in moving fluid from this through through this distance delta x1, and it is the F1 that is responsible there. So the W1 must be F1 times delta x1. I'm going to write comma and do the W2 here so we get more space. W2 equal to what? So, one thing here I want to explain. F1 and then this part also, this ball fluid move from here to this side. So both of those force and the change in displacement, they are happening in the same direction, okay? So we have a positive value here. Now important thing here, W2, look at this guys. The force due to pressure is actually on this direction, okay? Because we looked at that pressure before the fluid was even moving, okay? So that's when we looked at the pressure. So pressure is just force by area. But then that force is actually in this direction, and but then it is now moving through the distance delta x2. This change in the displacement is happening opposite to the direction of the application of pressure force F2. So we must have negative work done there, which means minus F2 delta x2, okay? Now we can see the total work done W equal to W1 plus W2, right? Total work done is you always add total work done, but then we end up with what? F1. Instead of F1, what can we write? We don't really know what's the value of force here, and then we are talking about the pressure. So in place of F1, can I write P1 times A1? Okay, I think I can do that, right? P1 times A1 times delta x1, instead of plus it's minus here, now P2 A2 delta x2. So now this quantity here, area times the change in the displacement, A1 delta x1, A2 delta x2, this quantity here. Can we write as delta V? We should be able to write that, right? So this becomes simply what? P1 delta V minus P2 delta V. Oops. Delta V. So let's call this as equation 4. Okay? So we have everything we need so far. Let me check my video whether it is recording or not. Alright, it is recording. Okay, so I'm going to erase this part here. Maybe which part shall I erase? Okay, yeah, this part I think is okay. So what we are going to do is get the value of this delta k, this part here, get the value of delta u, this part here, and get the value of w here, and then put it in this equation here, okay, equation number 1. Okay, so I don't really need this part here, right? So if after we substitute the value, we can say delta k is what? So half rho delta v times b2 square minus half rho delta v b2 square plus delta u is what? Rho delta v z y2 minus rho delta v z y1, and this value must be equal to total work done W, that is equal to P1 delta v minus P2 delta v. Okay, so I'm going to erase all of these guys. Alright, alright guys, so let's look at a few things here. Can we cancel anything here? Do you see anything common here? This guy here, delta v, delta v, delta v, delta v, delta v, delta v, and there this is after equal sign. So delta v is common, so we are not going to write it again. Why spend time writing it, right, if we don't have to? So just let's write the other things other than delta v. So rewriting equation, we get half rho b2 square minus half rho b1 square plus rho z y2 minus rho z y1. I'm going to erase this also. I'm going to write it in one single line. Equal to P1 minus P2. Oh, this looks more neat now. Alright guys, so since we have the subscript 1 and 2, let's do this. Let's rearrange this equation so that everything that has to do with the point 1, let's put it in one side, and then let's do the same thing. And let's put the, all the quantities that has to do with point 2 in the other side, okay? So since I have this as a positive here, so I'm just going to move P2 here on the right hand side, sorry, left hand side. So I'll get P2 plus half rho B2 square plus rho zy2 equal to P1 plus half, right, this when it goes there it becomes plus half rho B1 square plus rho gy1. Alright guys, so I'm going to put this in a box and call this Bernoulli's equation.